Hi, my name is Nur Nafisa binti Muhammad Azhar. I'm from Polytechnic Sultan bin Zainal Abidin and I'm from Department of Mechanical Engineering. Today I will present about a preliminary design for an IoT-enabled automated biodiesel processing reactor for the conversion of waste cooking oil into biodiesel. Abstract. Biodiesel as an alternative to diesel fuel offers unique properties that make it an attractive option. These properties include significant reductions in greenhouse gas emissions, non-sulfur emissions, non-particulate matter pollutions, low toxicity, and biodegradability. Biodiesel is essentially a monoalkyl ester of long-chain fatty acids and shares many characteristics with fossil fuel-derived diesel. It can be produced from various sources such as vegetables oils, animal fats, and other feedstocks, with WCO being a particularly valuable source. However, the extraction process from waste cooking oil is labor-intensive and requires expertise to manage chemical mixing, stirring, heating, and product washing in each production batch. This research aims to develop an automated portable biodiesel processing reactor with an IoT system that minimizes human intervention while maximizing biodiesel yield and production efficiency. 3 designs were proposed and evaluated using a book MaTRiX, which led to the selection of the third designs as the final choice. This preliminary design includes tanks, pump, mechanical stirrer with motor and temperature sensors. In conclusion, the preliminary conceptualization of the biodiesel processing reactor fulfills the requirements of efficient biodiesel production. Introduction. Concerns about pollution, global warming, and oil shortage are driving the search for cheaper, eco-friendly fuels. Biodiesel can come from various edible and non-edible oils, but production has challenges including quality control and distribution. More than 350 crops have been used to make biodiesel, but only a few are practical due to limited production. Using more biodiesel can reduce oil imports and boost local economies, but it might also raise food price and reduce food supplies. Biodiesel properties vary by country because of differing regulations. Figure 1. A schematic figure of the transistorification process. Reduce carbon monoxide, hydrocarbons, and smoke emissions due to higher oxygen content. Has minimal effect on nitrogen oxide emissions. Results in lower engine cooling oil and exhaust gas temperatures. Doesn't affect engine start up in hot or cold conditions. Increase brake specific fuel consumption due to lower energy content, but maintains thermal efficiency similar to diesel. Blending biodiesel with conventional diesel reduces emissions without affecting fuel injection. Step in producing biodiesel from WCO. First, gather the used cooking oil from restaurants or homes. Filter the oil to remove impurities. These include food particles and water. Heat the filtered oil to get rid of any remaining moisture. Mix the heated oil with alcohol, usually ethanol, and a catalyst such as potassium or sodium hydroxide. This chemical reaction breaks down the oil into biodiesel and glycerin. Let the mixture cool. During cooling, glycerin will separate from the biodiesel. This is because glycerin is heavier and will settle at the bottom. Remove the glycerin and clean the biodiesel to get rid of any leftover contaminants and extra alcohol. Finally, perform strict quality checks to make sure the biodiesel meets all necessary standards. Figure 2. Process flow diagram of overall biodiesel production process. Problem statement. Flat bottom tanks are less suitable for use due to their inherent design flaws. Reliance on human labor and supervision in manual systems can lead to a range of risks and inefficiencies. Manual tasks often require additional time due to their multi-step nature and the need for continuous supervision. Objective of study: to design the automated biodiesel process reactor system, to fabricate and develop the automated biodiesel processor reactor system, and to analyze automated biodiesel processor reactor system. Methodology: in most cases, it will include detail the main products, production rate and purity requirements, as well as any limitations that will affect the design, such as details on potential processes and the required unit system, details about the terms, cost, and accessibility of utility service. The following goals of the study is to designing the biodiesel processing reactor, developing the waste cooking oil to biodiesel conversion process, evaluating design capability and performance. Designing the WCO biodiesel processing reactor. Figure 3, flow chart for the automated waste cooking oil WCO biodiesel processing reactor. Figure 4, an example of process flow diagram of overall biodiesel production process. Figure 5, function decomposition chart. Idea generations. Table 1 shows the morphological chart for the selection 1, selection 2, selection 3, which is include the tank, material, microcontrol, stirrer, motor, power supply, solenoid valve, temperature sensor, flow rate sensor, and pressure sensor. Idea concepts. First, design selection. Table 2 show first design detail. First, use 3-cylinder tanks to store the glycerin, washing water, and perfect biodiesel. Then, frames are used to support the tanks. Use a fluid pump to suction and deliver the fluid. One stirrer is used for the cylinder tank. Next, the motor is attached at the top of the stirrer for the mixing tank. Then, use a microcontroller to monitor. Use a valve to control fluid flow. The biodiesel is stored in the storage tank. And lastly, use 4-cylinder tanks, WCO, methanol, potassium hydroxide, and distilled water. Table 3 shows the second design detail. First, frames are used to support the tanks. Then, use a microcontroller to monitor the process. Use 2-cylinder cone tanks, methanol plus KOH and WCO. Use cylinder cone tank. The heating and mixing tank is equipped with a stirrer, timer, and motor. Then cylinder tank with pump to deliver distilled water. Cylinder tank as the storage tank for glycerin. Cylinder tank as the storage for washing water. And cylinder tank as the storage tank for perfect biodiesel. Table 4. Third design detail. First, frames are used to support the tank. Then, use Arduino Uno as a microcontroller to monitor all the processes. Next, use 4 small cylinder cone tanks, 1 large cylinder cone tank, and 3-cylinder tanks. Use a cylinder cone tank as a primary mixing heating tank. The motor, stirrer, sensors, and timer are attached to the mixing and heating tank. WCO, methanol, KOH, and distilled water. 4 small cylinder cone tanks are attached solenoid valve and timer at the bottom at the tanks. 3-cylinder tanks are attached with a solenoid valve and sensor. Table 5 shows the design selection matrix path matrix for 3 various processing reactors. Final design selection. Figure 5 shows an automated waste cooking oil biodiesel processing reactor isometric view. Figure 6 shows an automated waste cooking oil biodiesel processing reactor, which A front view and B side view. Conclusion. The concept of an automated waste cooking oil biodiesel processing reactor was intriguing overall. Throughout the development of this project, numerous original ideas have been contributed and discussed. However, a few innovative ideas had to be discarded due to funding and time constraints, as well as a lack of expertise. Overall, the project's goals were achieved with the selection of the final design, which was chosen through a process of idea generation. Thus, a few key points are highlighted. First, this an automated waste cooking oil biodiesel processing reactor may address the issue of used cooking oil by chemically converting it into valuable products, including biodiesel. Second, the path matrix was employed to determine the best option among the three proposed designs. So this is reference from our research of the biodiesel production. Okay, so that's all from me. Thank you.